start with the first presentation. Point, depth, count, multitask, medical image understanding with instruction, tunnel vision, language models, and presenter is Sushant Kata. Okay, thank you. The stage is yours.
AI is everywhere, transforming the way we live, work, and interact. It has been democratized. It is in your pocket. Every time you use Siri, Google Assistant, or even unlock your phone, AI is working for you. AI has impacted different fields, and clinical or medical system, it is also not left behind. There are different applications that have been developing, and there are researchers working on different domains in medical AI, trying to figure out how we can integrate this new technology in healthcare systems. So with the advent of multimodal AI, there have been rise of these vision language models or VLMs, so which has huge potential in transforming biomedical AI. Let me introduce myself. I am Sushant Gautam. I am a PhD student at Simula in Norway, and now I am doing my research stay in LA Institute in London, and I am presenting my recent work. It's called Point, Detect, and Count. And with this work, we want to see how these VLMs or visual language models do with these fundamental tasks like pointing, detecting, and counting. So let's begin. So to start with, I will start with this dataset. It's called Quasir VQA. It's a visual question answering dataset that I was working on with. It's a question answering dataset. So you have some images, and there are different types of images. And for each images, you have question and answer. For example, like there could be one image there, and it would have some class, and there would be some questions, and there should be some annotated answers by doctors. So it's a basic visual language task. So you have some computer vision modality like image, and you have some language that is question. So you ask LLM like what is there in the image, and it will give you answer. So this is one of the fundamental tasks that we do in LLM. But in medical AI, we need even more things than the general AI system, because in medical AI there can be no mistakes. It should be highly reliable. The answers should be clinically grounded. So we need to do quite more intensive things to make this medical AI system. So we got this inspiration. So we wanted to see how these models perform when we ask them to do basic tasks like detection, localization, and counting. Because these types of tasks are required in any genetic field, like in our human life as well, also in medical things. For example, for radiologists, for pathologists, or even like other medical tasks. So you need to count things in the image. For example, if there is some polyp in the image, you have to count how many number of polyps are there. Or even like if you want to do sperm counting, so you have to, there are machines that does this kind of thing. So in different domains we do this kind of thing. So we want to do this with VLMs now. So there are existing medical visual question answering systems made with QA. So there are also datasets that are designed to make this system robust. But these question and answers are very simple. So they are not that complex, and they are definitely like related to this clinical task. And one thing is that they are not structured. By structured, I mean it's some format like XML or JSON, because language model they give big sentence as output. For example, if you have ChatGPT, it will give you some text as output. But if you want to use it on other downstream applications, so you want some structured format like coordinate x1, x2, y1, y2 kind of thing. So these kind of things are lacking in this made with datasets. So in our work, we want to expand our clinical applications to this structured format. So we take 3 different data sources. So as you can see, the pictures they are not that good because they are for medical and inside the body. So the first one is from Quasir dataset. So there are pictures that has instrument on them. So while doing some endoscopy, they use some instrument. So these instruments are there. And on the second one, we have some polyps. So these are the good things that you want inside your body. And on the third one, this is sperm. So it's from sperm tracking dataset. So there are sperms that is annotated by the red and greens. So we have 3 different datasets, and we want to formulate 3 different tasks, the fundamental tasks. The first one is pointing. So in pointing tasks, you ask questions like where is the polyp, and you want the model to give you single coordinate. It should be like x, y, 2D coordinate. And another task is it's like detection. It's a very classical computer vision task. So you ask like where is olive or where is cat, where is dog, and you want your model to give you bounding box. It's like a rectangle. So this is like bounding box detection. And the third one is counting, very trivial one, right? So you just ask the model how many these things are there, and you want model to give you some integer number. So these are three different tasks we formulate. So we have 10,600 images from three different classes, and we have multi-task. So we have three different tasks, and what we are trying to do here is that we have individual tasks, and we also formulate combined tasks. For example, you want combine localization and counting together, or like detection and counting together to see how it performs. So I'll get into more details later on, but this is the overall thing that we are doing here. So it is addressing stereoscopy and microscopy domain, and it's designed for this visual language model. So yeah, this is the data set. So it's very multi-points because there are like different tasks in different points in different data sources here. So we use this data set. And we want to make sure that these VLMs can do more than just visual-based answering. We want them to be used as annotators so that it can be used in different clinical workflows, and so that we can use VLMs to make them output structured formats so that they can be used for different applications. For example, like if you want to have some bounding box drawing, then you would want some output format, not just text, so not just descriptions. That's why we have this formulation here. Okay, this is the overview of data set. For example, like this is our open source. So the annotation is like this. For example, like for this image, there is like point. So in point it is 2D, like it's just x and y. So in bounding box it is x1, y1, x2, y2. It's like rectangle, and in count it is just a number. So in this image there is some problem. So what problem is there? It is another tables. But like usually there are three things here: point, bounding box, and count. So yeah, this is what is in the database. Data set. Now in our work, point, detect, count, we fine tune our VLM. So the name of VLM is point 2.5. It's like 7 billion parameter model, and it is the one from Alibaba research. So it is the latest one, like it's state of art open source model, and then it does like real. So you can just input image and text there, and like you can expect it to give you some text output. So we fine tune that model to do this task. So the task is like the three tasks that I mentioned here. And the way to ask questions to this model is you can only ask in textual format. So for example, you have a medical image here. So you give some prompt there. For example, you say, okay, detect poly and output in JSON. Like it is inherently doing that. So this is what you do. So this is here. So there will be vision and text. So it passes to vision encoder, and there is some model that is fine-tuned for this task. And at the end, you expect it to give you some output in instruction format. So usually it is JSON format. Even in other tasks you want, if it is, for example, it is a bounding box detection. So if you ask it to do bounding box detection, it will give you in that format with like x1, y1, x2, y2. It's a bounding box rectangle. So that you can even use it for evaluation because it is already structured. So it's kind of like classical detection task. So yeah, this is how it is formulated. So generally, for example, if you have to do the same task using other workflows, because here are three different domains here. It is and it is doing three different tasks. So you would need individual model fine-tuned for that individual task for that individual domain. So as you can see, images are there. For example, for detecting swarm, you would need a trained swarm detector. For detecting poly, you would need a trained poly detector, and also for the instrument, it should be very different. So what we are trying to do here is like we are trying to build a generalist model, a single model that can do on different domain, and also that can do different tasks at once. Because, for example, if you call back this classical detection models using like CNNs, it can only do one task at a time. It cannot do multiple tasks. But with this approach, we can maybe do multiple tasks across multiple domains. So we fine-tune this model on 10,600 annotated images with the approach I mentioned. So usually the instruction is like what you want to just write it in text. For example, like you can actually do it on bounding box and a total count at once. If you want like multiple output, you can do it. For example, you can ask 2 at once or like single at once. So this is how we do it by natural language. And we expect expect that this approach it will be able to handle two tasks simultaneously. It's not like a classical CNN, like where you ask it for like detection and it will give you only bounding box coordinate. This can do two at once. You can count and like it will give you like bounding box coordinate at once. So we use LoRa as fine tuning because this stable binaire product is like it's very used. So we just want to fine tune the layer that maps the designing model to language model part. So this is what we do, and this is the result. So it is a lot of things here, but I will try my best to explain. Okay, now let's start with the counting task. So it's a very trivial task. In this task, you ask model like how many count of some problem is there. For example, how many count of polyp is there, or how many instruments are there. So this is a very simple task. So these are some metric. This is MAE, is like error. Like display error. So this is point public. This is the public checkpoint that this Alibaba research released. So it is not fine tuned. So if you try this on this public checkpoint, then you get around like 9 MAE with just counting task. So if you just ask it to count, it will have some errors. You can see the magnitude of this error. But if you combine two tasks at once, for example, if you ask it to count and to point at once in a single prompt, then it will give you like two answers at once in a single prompt, and the error in counting will be around 6. So as you can see that the error is reducing here. And also if you ask counting and bounding together, so if you ask it to count as well as if you ask it to output the bounding box in a single prompt, then error is reducing. So it is a very crucial finding that motivated us to explore this thing. Because what we initially thought was like if you make the problem complex, it will be difficult for model to output the results properly. But we are seeing opposite here. That's why this paper is here. So if you ask a simple task counting, then you are getting this magnitude of error. But if you combine the tasks together, like if you make it more complex, because outputting a bounding box is more difficult than just counting, isn't it? So when you combine it together, the error in counting part will be less. So yeah, this is the main finding of this paper. This was the overall inspiration that we tried. So the conclusion that we can get from this result is that in VLM, so if you combine tasks, if you make it multitask, it tries to figure out like more features and like it understands the input modalities better. So this is the finding. Now we continue that with pointing task. It is not the same finding cannot be like generalized to all the tasks, but in counting it is so. But in pointing, as you can see here in the pointing only task, so if you ask it to only output 2D coordinate, then the error is in this magnitude like 52. But if you combine it with pointing, if you ask it to like count and point together like in before, the error in pointing task will increase. It's not that high, but like it will change. Yeah, this is what we found. And in detection, if you just ask it to detect, and if you just ask it to, if you combine counting and like bounding box detection, it's very low because it is not fine tuned for medical purpose. It is a general purpose model. So the errors are very less. So it wasn't really useful because it was almost useless. So we tried to fine tune this model. So this is our model. It is like fine tuned using LoRa. It is the same model fine tuned for medical tasks using our data set. So this column has our results. So you can see that in counting tasks, if you fine tune it properly, the error reduces like to almost 0. So it's very useful. So similar results are seen in like combined tasks. So if you combine counting and pointing, like the errors are very low. So yeah, this will help. So if you do multitask training, so it can help you a lot in making it understand our domain and like our problem. Now the same thing for pointing. So in public checkpoint, this was the magnitude of result, and in our checkpoint it is very low. It's almost around 0. And if you combine, yeah, the errors are a bit higher than before, but it's still lower than in the public checkpoint. So yeah, this is what we see here. And the same for detection task. The scores in public checkpoint was almost 0, so it is very useless because we want the precision to be higher. But fine-tuning model, they show very high precision. So these are very higher numbers. As you can see, it's almost around like 85, 95. So if you combine these tasks together with bounding, that is, if you make it more complex, then the scores are still higher. It is a bit less than a single bounding detection task, but if you combine with counting, it is around like 80, like almost like around 90. So yeah, this is also very useful finding, and this is what we figured out. So to summarize the result, we figure out that if we fine tune these VLMs, definitely they are meant to be fine tuned for the domain. So if you fine tune this make massive improvements over the public checkpoint. So it can be used for different scenarios and different domains. And we see that if we fine-tune it with joint tasks, if you combine two tasks, like even three tasks, then you can see that the performance is good enough. So, and also it is consistent. It's not like you can combine any task and you see good performance increment. We see one peculiar finding that there were some zero case. We call this zero case because if there are some other problems, the VLMs were trying to cheat. So instead of giving some structured output, they were just trying to give you some like unstructured text. So they will just say like, you know, the problem wasn't in the image, or like they will come up with natural text as natural sentence as output, but we want in JSON format. So they were failing to do so. So we also have this in some hard example cases. So yeah, despite limitations of VLM, like they are improving, so it could be solved like newer iterations of architectures. So we see that they can perform structured reasoning if they are properly prompted and fine-tuned, and unified models trained in multitask. They can reduce dependency on task-specific architectures. You don't need to have different architectures for different tasks. So you can have combined architectures that can address different domains at once, like different tasks at once. So these models not only generate text, for example, like ChatGPT, you expect it to give like long description of text, but like these models can also output structured JSONs, and they're almost guaranteed so that you can use it in downstream tasks. And these models could also be made more robust using some vision augmentation or even like text augmentation, so that they can be more aware about the complexity and show in the evaluation. So fine-tuning general VLMs with task fusion, like with multitask fusion, it unlocks powerful multitask medical AI. So we can imagine a future where we have a generalist model that is able to perform different array of tasks in different domains. So we can dream of that future from here. So a single model, it can handle different tasks. Like they are very trivial tasks as of now, but like it can evolve to hard tasks. So it is a detection, counting, localization, and combination of these. So it can have very highly accurate and structured output for different data types. And this is a path to explainable and efficient clinical tools development. So this is the takeaway of this. So I end up my presentation. So if you have any question.
Okay, thank you for the presentation. Are there any questions from the audience? Okay.
So I have a question for you. You said in the presentation that you choose this kind of architecture because if you had choose something related to syntax and then I go only to perform one single task at a time.
Yeah.
Did you compare the performance with the kind of architecture?
With other architectures?
Yeah.
No. It was just on this particular one. So we just fine-tuned it because it was the best model. It is still the best model. So like so we didn't try it with the less powerful ones, because there are, for example, if you try like other VL models, they are not. This is the best one. So we expect that like the models, other models like the performance should be great there. So yeah, we just tried on the state-of-art ones. So yeah, that's the thing.
Yeah. My question is about, did you include a sort of medical extraction of the result that you obtained?
Yeah, definitely we did, because yeah, the data set is already medically annotated. So it's like, for example, like the bounding box and all these things, they are annotated by clinicians. So we compared the objective scores. So I mean, they are kind of like binded from that. So it's
Okay. Okay, thank you.
yeah.
Okay. Let's thank again the speaker.